If you place a typical bar magnet close to another, they will attract or repel each other depending on which way their poles are facing. The worldly wisdom is that north attracts south, and same poles repel. But this is merely a description. What is physically happening at these ends? Michael Faraday proposed that the lines of force that constitute a magnetic field are real, and James Maxwell said that there is matter in motion in that space. Indeed, a magnetic field is definitely comprised of moving matter of an exotic nature. This becomes evident when you realize that a magnetic field has the ability to pull one iron filing at a time when underwater. These lines of force sweep around the outside of a magnet and through its center. They flow into the South Pole and come out of the North. The fields of two magnets merge during attraction. The task then is to identify the physical medium, the secret agents that constitute the magnetic field. The rope hypothesis proposes that any two atoms are bound by an entity that resembles a rope, a twined pair of threads. All atoms in existence are physically connected. Under this model, electricity consists of a string of atoms that have merged to form a serpentine. This serpentine spins in place. Keep in mind that under the right-hand rule, the magnetic field runs perpendicular to the electric field. The serpentine spins very fast and induces threads to separate from the rope they formed. The rope model of magnetism proposes that Faraday's lines of force are physical threads that acquire our everyday macro-world property of touch by aggregation. Countless threads form the magnetic field of a magnet. Let's now visualize how these swinging threads produce attraction and repulsion. We begin with an analogy to get a grip on the basic mechanisms. Imagine two brothers, Axel and Rod, skipping next to each other. Their ropes are swinging clockwise. The ropes interact. Axel and Rod are drawn toward each other as a result of this interaction. Rod now turns around and faces Axel. Their jump ropes now clash and push each other away. Let's now extrapolate these mechanisms to magnets. It is misleading to divide a magnet the traditional way, into north and south poles. In order to understand the mechanisms of attraction and repulsion, it is more profitable to divide a magnet into top and bottom halves. Consistent with our experience with lines of force, the threads on the top half swing around, enter the traditional south end, slide along the interface between top and bottom halves, and come out the traditional north pole. The threads on the bottom half sweep around in the opposite direction, in a mirror image of those on the top. Let's now look at what happens at the four corners of two magnets that face each other north to south. On the top half of the first magnet, the threads are swinging counterclockwise. On the top half of the second magnet, the threads are also swinging counterclockwise. The threads on the first magnet come up and latch on to the threads of the other magnet when they come down. The threads on the bottom half of the two magnets swing in the opposite direction. The threads of the first magnet swing clockwise, and those of the second magnet also swing clockwise. The threads of the first come down and latch onto the threads of the second magnet, which are coming up. The threads go through each other despite a faint subatomic friction. The more threads that intervene, the stronger the attraction between the two magnets. The number of threads that participate is a function of distance. If we turn the second magnet around 180 degrees, the threads on top and bottom halves now swing in opposite directions and clash against each other. The farther the magnets are apart, the fewer threads that intervene, and the weaker is the strength of the repulsion. The rope model of magnetism explains the invisible mechanism that underlies attraction and repulsion.